Resistance is a measure of how much a component in a circuit resists the flow of electric current. It's measured in ohms. Ooh. Various factors, including the material, temperature, and physical dimensions of the component, can affect resistance. But in some special components, resistance can also be influenced by external conditions like light intensity and temperature. An LDR, or light-dependent resistor, is a type of resistor whose resistance decreases as the intensity of light falling on it increases. It's made from a semiconductor material that exhibits photoconductivity. In darkness or low light conditions, the LDR has high resistance, often in the megaohms (MO) range. When light shines on the LDR, photons are absorbed by the semiconductor material, freeing electrons and thereby increasing its conductivity. This causes the resistance to drop significantly. Some applications of LDRs include automatic lighting, street lights that turn on automatically at dusk and off at dawn, use LDRs to detect light levels. Alarm systems. LDRs can be used in security systems to detect changes in light levels, triggering alarms when light is blocked or altered. Light meters, used in cameras and other devices to measure light intensity. A thermistor is a type of resistor whose resistance varies significantly with temperature. There are two main types: negative temperature coefficient, NTC, thermistors, where resistance decreases with increasing temperature, and positive temperature coefficient, PTC thermistors, where resistance increases with increasing temperature. At low temperatures, NTC thermistors have high resistance. As the temperature rises, more charged carriers become available in the semiconductor material, reducing the resistance. At low temperatures, PTC thermistors have low resistance. When the temperature exceeds a certain threshold, their resistance increases sharply, making them useful as current limiters. Some applications of thermistors include temperature sensing, used in digital thermometers and temperature sensors in various electronic devices. Overcurrent protection. PTC thermistors protect circuits from overcurrent conditions by increasing resistance when too much current flows through. Temperature compensation. Used in circuits to compensate for temperature variations and maintain stable performance. Sensing circuits utilize LDRs and thermistors to monitor environmental changes and trigger specific responses. An LDR can be part of a simple circuit with a transistor and a relay. When it gets dark, the resistance of the LDR increases, causing the transistor to turn on and activate the relay, which switches on the light. Operation. As light intensity decreases, the voltage across the LDR increases, reaching a threshold that triggers the transistor and activates the light. An NTC thermistor can be used in a temperature sensing circuit. As temperature rises and resistance drops, the voltage across the thermistor changes. This change can be used to trigger a comparator, which turns on a heating or cooling system. Operation. The circuit is designed to maintain a set temperature. When the temperature deviates from the desired range, the change in resistance alters the voltage, which is detected and used to adjust the system. Imagine you are designing a smart greenhouse. To ensure optimal plant growth, you need to monitor and control the light and temperature inside the greenhouse. You install LDRs around the greenhouse connected to automatic shades. When the sunlight is too intense, the LDRs detect the increase in light intensity. Resistance drops, sending a signal to a controller that lowers the shades to protect the plants. You place NTC thermistors in various locations to monitor the temperature. If the temperature drops too low, the resistance of the thermistors increases, triggering the heating system. Conversely, if it gets too hot, the resistance decreases, activating fans or opening vents to cool the greenhouse. LDRs and thermistors are incredibly useful components in electronics, allowing circuits to respond dynamically to changes in light and temperature. By understanding how their resistance varies with environmental conditions, engineers and hobbyists can design systems that automatically adapt to their surroundings, enhancing convenience, safety, and efficiency in various applications. Whether it's turning on streetlights at dusk or maintaining a stable temperature in a greenhouse, these components play a crucial role in modern sensing circuits.